Starting a new conference series requires a lot of efforts, and one of the most important things is how to choose plenary speakers. This was already mentioned before, and for this conference a whole great set of speakers have been assembled for the conference that also contributed, of course, to the attractiveness of this conference. The first speaker today is very special. Namely, our first speaker today is not only just a great plenary speaker, but our first speaker can be really said to be the father of modern control, or at least one of the fathers of modern control, the inventor of the Kalman filter. And I believe that it would make little sense to repeat here where he got his bachelor degree and his master's degree, because his contributions are so much more bigger. And therefore, I'm just giving the floor to Professor Rudi Kalman, please.
Thank you very much for your very kind words. I hope you'll excuse me for sitting here during a lecture, but I think the microphone is more effective if I'm always in the same position. I'm very, very happy to be here in this city today, because it was the same city where I first set foot on the soil of Russia exactly 55 years ago, staying at the Astoria Hotel for 2 nights before going on to Moscow. What I'm going to talk about today is, in my opinion, of the utmost importance and promise for the future. It's a totally new look at the basic problems of systems, talking about old methods, solving old problems, but at the same time very modern in its implications for the future. I'd like to have the second slide, please. Okay, I first have to explain what I mean by the title of the lecture, and this is fairly obvious, but it does require some further explanation. The problem is this: we are given some sort of a physical system, possibly even a human being, and we observe its behavior. That is to say, we are able to say what happens to this system under various conditions, such as inputs and outputs. And the issue is, how much do we learn about the internal structure of the system from observing its behavior? I was quoted several times about a certain general statement that I've been making in various forms for many years, namely, if you know the physics of the system, and that of course rules out human beings to a large extent, then if you want to know anything more about the system than the basic physics, you must use mathematics, because there's no other way of going more deeply into that problem. Now, there are many historical examples of this problem. It's basically the problem of natural sciences, if you like. The worst example is a chess-playing machine that was very sensational in Vienna, about 200 years ago, where a machine was able to play a very high quality chess. Unfortunately, it's a bad example for our purposes because after a great deal of sensation and interest in the thing, it turned out that inside a big box holding the chessboard and so forth, there was a midget who was a very good chess player. So this is not a good example to work on. Another bad example is the great physical advance of Röntgen, because that is not really the same problem. It's a brute force, rather nasty way of trying to penetrate into a system. We're not talking about anything like that. We are only interested in the normally observed behavior. We don't want to interfere with the system in any physical way, and we certainly don't want to change anything inside by our observations. And of course, today there is a version of the chess-playing machine requiring a rather large computer, and the problem would be to find out what the program of this computer is. But for that purpose, you'd probably have to play millions of games, and therefore it's not a particularly useful example, although it's a goal for the future. Let's have the next slide, please. Now, among good examples is a paper by Betrand Russell, published just before World War I and republished at the end of World War I, called Mysticism and Logic. It's a reference I only learned a few months ago, which concerned the basic problem of how to construct a physical knowledge, a physical theory from so-called sensory data, which is the same thing in my terminology as observations. And he said essentially the following thing. I'll have a full quote in the written version of this talk. He said that you first have to know how a physical system produces the data, the behavioral data, and you have to have it in mathematical form. For example, Kepler's laws of planetary motion would be a very primitive example of the same thing. But then you have to invert these equations. And that was the end of the paper, more or less. And now, more than 100 years later, we have really to become serious about this problem of inverting the behavioral data, and the main results I'm going to be talking about is exactly what is involved in this inversion process. It's far more complicated than the inversion of, say, a matrix. Another example is my former late countryman Eugene Wigner, who wrote an interesting paper around 1958 saying, discussing what in his eyes was the unreasonable effectiveness of mathematics and physics. If you take Russell's article, which was certainly not known to Wigner, one would phrase it somewhat differently, namely the difficult mathematical problem presented by effective use of mathematics in physics. There was a great deal of discussion on this paper of Wigner, but without any conclusions. I even talked to him personally about it. But it's basically a point along the way to the problem I'm going to talk about. Then there is also the famous Yakubovich-Popov and I modestly add Kalman lemma, which goes back to a very important work of Brunner in 1932, which is at least tangentially involved in the same thing. The problem was how to characterize those behaviors which correspond to a passive linear system. And finally, we have the empirical fact that the so-called Kalman filter, which is a rather crude but logically consistent attack on the same problem without any great mathematical depth, as an approximate model has had huge practical success. For example, the GPS system today has enormous accuracy, and in the future the accuracy will be even better, and has something like 1.5 billion users. So it's clearly a property of humanity and not of any particular country. In fact, in America, in Japan, and Europe, there are big engineering efforts on the way to extend the usefulness of this approximate solution of our basic problem further and further. I'd like to have the next slide, please. Okay, there is one basic theoretical result of which I'm very proud, namely that under very precisely described conditions, it is known since about 1960 that if I look at the behavior of a linear so-called time invariant system, then I can have a direct correspondence with the behavior only under a specific condition on the system, which is a condition of being completely controllable and completely observable. This thing was arrived at by a lengthy analysis of all sorts of things, but essentially this is a very basic property, and the only unsettled question at the moment is what to call it. So sometimes it's called minimal, irreducible, canonical, intrinsic, or generic. I prefer to call the property generic because it essentially means that if you make any change in the system whatsoever, then the result is no longer, the condition is no longer valid. So generic means sort of the simplest, the most intrinsic way of describing a system. The intuitive idea of the system is very simple, namely, if there is a general system, it can be decomposed into 4 parts. One is the basic, completely controllable, completely observable part, and this part is completely, maybe completely controllable, could be completely controllable. This is completely observable, and this is nothing, it just sits there. So obviously it has nothing to do with the behavior. The main result I'm going to talk about is an extension or an abstract analog of the same result in a rather different context, but conceptually very similar. Let's please have the next slide. The main limitation, there are 2 limitations of the previous result. One is that there's a unique correspondence between the system and its behavior, provided the system is generic, in other words, completely observable, completely controllable. To obtain, to go further, it's very interesting to note what happens when we know something about the possible components in the system. The previous result is general for all linear systems. The specific system I have in mind is a classical example of a passive electric network consisting of resistors, capacitors, and inductors. and possibly some other passive elements, for example, an ideal transformer. For the purposes of this analysis, however, we shall assume that there are only three components, R, C, and L. Now, the problem posed here is very much more general than the specific example of passive electric networks, and I think for the purposes of some intuition, it is useful to look at atomic physics, in particular the periodic table, in which, again, according to the physicists, there are three components, namely a neutron, an electron, and a proton. You might think that this is a completely far-fetched type of speculation, which it might be in the long run, but at the beginning it does make a certain amount of sense because, according to, again, the physicist, the atomic physics is governed by quantum mechanics, and quantum mechanics is a linear theory, and the basic results of physics are that we have discrete particles, at least on the level of looking at the periodic table, and therefore it could very well be that we can say more about the physics by the new methods than was possible before. In any case, what is involved is looking at a situation where we know that there are finitely many elements composing the system and giving rise to the behavior. So the question is, what can we say about these elements in the system from the behavior itself? And that is a problem that has never been posed before, to the best of my knowledge, with the exception of some newly rediscovered work of Ronald Foster that I will refer to later. In terms of historical background, I should also mention that this problem was known classically, that is to say 50 to 100 years ago, as a problem of network synthesis. And when I was a student at MIT, I had thought of doing a doctoral thesis in this particular area. Fortunately, while I was very immature, I was not completely stupid, and I did not do a doctoral thesis in this area, which, if I knew what I know today, would have resulted in instantaneous world fame. But I didn't know at that time what I know now. So, and in fact, nobody that was on the scene knew anything about it either, including my future doctoral supervisor. Okay, the next slide, please. Okay. Well, since this talk has a lot to do with mathematics, let me state the main result first without lots of motivation and so forth. The relevant area of mathematics that is directly and naturally involved here is that of the theory of algebraic invariance. So the theorem is stated in terms of this particular not old but not forgotten field of mathematics. Namely, given any such network, but ruling out ideal transformers, to be absolutely clear, we have the following situation, that from the behavior, one can compute a set of invariants and covariants. I'll explain what a covariant is and what an invariant is. And from such an information, which consists of so to say, algebraic data, in practice some polynomials or some equations with polynomial coefficients, one can obtain a complete solution of the realization problem. That is to say, one knows under conditions involving these invariants what kind of what are the elements inside the system, and also what possible configurations there can be, in particular what can be the graph of the electric network that is involved. For technical reasons, let me briefly mention that when you have a circuit diagram, it can be regarded as a graph, and the configuration of that graph, that is to say, the way that network elements are associated with branches of the graph, is what is conventionally called the network. So we can answer using invariant theory, based on this theorem, all the questions that can be asked, for example, when are two networks equivalent? Furthermore, it answers two basic objections to the main theorem on linear systems, namely, it is not necessarily true that you can uniquely identify what the system is, but you identify a finite number of possibilities, and you do not identify even the graph of the system, but there are a finite number of possibilities for the circuit graph to be compatible with the external behavior. Okay, the next. So let me say a few words about invariance. The one that is supposed to be the simplest notion of an invariant that's shown, that is supposedly taught even in high school, is a notion of a discriminant of real polynomial. The discriminant is a polynomial in the coefficients of a polynomial that you're interested in, and it decides whether or not this polynomial has only real roots or also possibly complex roots. This goes back to the roughly the middle of the 19th century, where a great deal of work was done on questions like that. So discriminant is a polynomial, as is shown on the slide, for a second order polynomial or equation, and if it is zero, it has special meaning. If it is positive, according to a certain sign convention, then it has only real roots, and if it's negative, it has also possibly complex roots. And that's true for arbitrary n. But when n becomes a little bit large, and that is to say, well, 3 may work, but 4 is becoming bad, and beyond that is becoming horrible, it is not an easy practical method to apply, but it is correct mathematics. The second question is, what is the, if we take two polynomials, do they have a common root? The gadget that decides this is called the resultant, which is a similar but much more complicated expression to the discriminant. And the mathematical essence of the 19th century work, which is now being resurrected, is that there are matrices whose determinants are the same as a resultant, the same polynomial. So the best known such thing is the Sylvester matrix. Its determinant is 0 whenever two polynomials that are involved in the construction of the matrix have a common root. There are other matrices of that sort, for example, the Bézout matrix. also its determinant again is the same as the resultant. And others, for example, the Hunkel matrix, which is well known in linear system theory. Another kind of invariant is the, for example, the minimal polynomial of a linear dynamical system that is very well known in linear system theory. However, the difference is that we have now a much larger variety of invariants to discuss and give much more detailed information about the nature of a system. Now, it's very well known classically that in addition to invariance, we have also things called covariants, which are equations whose coefficients are invariants. That are necessary to have a proper mathematical framework for the main result that I have talked about. Now, there is, of course, a condition involved in the main theorem, namely that invariance and covariance characterize in practically complete way an electric network in terms of its behavior. I should mention, which is not on the slides, that the behavior of an electric network is the same as its, of a one-port electric network is the same as its impedance. That is to say, if you put such a network into a bigger system, its behavior in the bigger system depends only on the impedance. The impedance was a brilliant idea of Heaviside around 1900. It gave rise to operational calculus, which was later on greatly expanded and improved. And in modern language, it amounts to algebraizing the problem, that is to say, replacing the solution of, for example, differential equations by algebraic conditions. This is one of the biggest trends in modern mathematics today, and it was already understood from outside of mathematics by Heaviside. Now, the main condition for the theorem is that you have to have a generic network. For example, if you have a resistor, a single resistor is generic. On the other hand, if you have a parallel or series combination of two resistors, obviously not generic, because from the terminals, which are in these hollow circles, you cannot tell whether what you see is a single resistor or multiple resistors. Therefore, such things are not generic. That's trivial, but the problem is that you need a general definition of generic networks. And you have, for example, here, a situation where there are two networks that have equivalent impedance. Of course, it means that given the capacitor and the two resistors in one network, there's a complicated formula that gives you the capacitor and the resistors of the other network so that the behavior of the two is identical over all frequencies, if you like. In this particular case, this is very well known. If you buy a so-called RCL meter, the operating instructions involve this equivalence. But the question is, why are they generic? Well, it's best answered by taking a version of it which is not generic, namely, if you put an extra resistor here so that this network contains both this and this, that is no longer generic. And intuitively it can be stated by saying it has too many resistors. Now, what a general generic network is currently an unsolved problem, because, except in an abstract sense, because you would like to have some sort of a criterion on the level of circuits, not algebra, that does this, and such a criterion is currently not yet known. On the other hand, there are precise algebraic conditions which will apply to the network, and these conditions are not very elementary. Another example is of the situation is the next slide, where these two networks are equivalent. Unfortunately, in the second network, the middle circle should be solid. Only the outside circles are hollow. And in this particular case, the so-called Y-delta transformation, which is well known to power engineers and so forth, will tell you that the two must be equivalent, but to get the exact formulas for this equivalent is far from a triviality, and it's usually badly presented in the existing textbooks. So at the moment, we have no explicit criterion in terms of graphs for the word generic, but the concept of generic is about as solid as you could possibly be in this context. Now, the question is, what is the behavior of such a network? Well, as I mentioned, behavior is the same as impedance. Could we have the next slide, please? And the impedance for all passive systems is given by an expression such as this. In other words, two polynomials with a restriction on the degrees of each relative to the other one. And the main mathematical comment is that the expression z is invariant if I multiply the numerator with a constant and the denominator with the same constant, because the ratio cancels out the multiplier. And such a thing is called a point in projective space. And the invariants we are going to talk about from the general theory point of view are nothing more than so-called projective invariants. In other words, there is a well-known theory that constructs all invariants of two polynomials where invariance is interpreted in the projective sense. So talk about projective invariance. Now, to give an idea of the machinery of how to do this, which is not easily available at the present time, but this is currently also being worked on, one has a formula for the impedance in the upper part of the slide, which is known in the current literature as the matrix tree theorem, but actually goes back to a paper of Kirchhoff in 1847 that was rediscovered around 1950. And essentially what you do is you look at the admittance yi of a branch of a spanning tree, multiply these admittances, and then obtain an expression for the admittance. But since I want to talk about impedance, which is a reciprocal of admittance, I need to put some messy symbols here. But in any way, this is an explicit algebraic map, always well defined, for the definition of impedance or its reciprocal admittance. The tricky part of the definition is that in the denominator of this formula, you are looking at the same thing as in the numerator, but with the case where a circuit graph is, the circuit graph is simplified by identifying, merging the two terminals that constitute the input terminals to the network. So that means it's a graph modulo the fact that one of the hollow circles is equal to the other hollow circles. This expression is discussed in many, many books on elementary circuit theory. I mean, this calculation of Z is discussed in many books in circuit theory, but the calculations are so involved and so nearly non-rigorous that you cannot carry the discussion any further. On the other hand, this formula, which is 150 years old, is immediately proves one thing, namely that since in a passive system the values of resistor, capacitor, and inductor are always positive, the formula automatically means that in the expression for Z, all the coefficients are positive or zero. So that gives an idea of the mathematical flavor of it, but the details are not too elementary, and the manipulation of this formula is quite difficult. Okay, so let's have a next slide. So if you want to have a sort of an intuitive idea of what's going on, Gilbert's very famous theorem of finiteness, namely a finiteness of the generators of invariance applying to very broad situations, including the present one, essentially means that everything is algebraic, and the question is to mechanize the computations as much as possible. Now, the computations are well known historically to be very unpleasant, but not undoable. Now, this gives you an idea of the machinery, but let me say a few words about the background of the problem. It was rediscovered independently by several people, including myself, that Ronald Foster, who was well known for a famous result called Petersburg theorem or something like that, a reactance theorem, published in 1924. He was a Harvard graduate with summa cum laude in 1917 and worked from that moment on at Bell Telephone Labs, and published the paper I'm referring to in 1924, which gave rise to the subject of network synthesis. It's the first solid result on the main problem that I'm talking about. It so happens that he was not a particularly good organization man, and during the war, when people were supposed to be working on military applied mathematical problems, he seemed to be uninterested in such a task, and therefore he resigned from Bell Labs, or that to say with his usual job at Bell Labs, and was transferred to New York to a subsidiary organization called Pioneers of America. I heard this story directly from Professor Gilman, who was my mentor at MIT. In other words, a classical example of the American method of kicked upstairs. But this didn't last too long, and he became a professor at Polytechnic Institute of Brooklyn, and continued working on a problem which is along exactly the same lines that I have talked about. As a result of that work, under the pseudonym of Edward R. Ladenheim, who was a naval officer and did a master's thesis under the supervision of Foster, he published his results, which consist of approximately 1,000 formulas in 50 pages that have to do with the explicit solution of the realization problem not using invariant theory, but essentially the same ideas as invariant theory. This was rediscovered by a group in Cambridge and maybe 1 year before that by myself, and is a basis of modern research. Now let me just say a few more words about why this is important. The next slide, please. Yes, okay. The issue is, how can we obtain insight from into the basic system by just using quantitative information about the behavior? It is, at least to me, a absolutely spectacular fact that in the situation I've discussed, which is perhaps closely analogous to atomic physics, you can obtain an exact result about the number of capacitors or the number of inductors in the system. The total number of capacitors and inductors is governed by the degree of the numerator of the denominator polynomial of the impedance. That's very well known and nothing particularly deep about it. But if you construct the Bézout matrix, whose determinant, as I mentioned, is the same as the resultant, and the resultant is not equal to 0, otherwise the problem is not well defined, then the signature of the Bézout matrix, which goes back to the 18th century, famous doctoral thesis in France, the signature of the Bézout matrix, which is real, symmetric, and has projectively invariant entries, gives you the number of capacitors and the number of inductors that are present in any generic realization of the system. In fact, even non-generic realizations. This is absolutely fantastic. I mean, to be able to, from the behavior, find out what's inside in detail the box is something absolutely unprecedented. If you look at the vague analogy with atomic physics, it might indicate, for example, questions such as isotopes, which presumably correspond to something like a radioactive isotope, correspond to something like a non-generic kind of realization of the system, etc., etc. So there's an enormous amount of possibility of what to do here. It should, however, be added as a note of caution that at the end of the 19th century, people were well aware of this particular generality of the situation. I should mention as a basic fact that the problem I'm talking about in connection with linear systems is a nonlinear problem. So you have a nonlinear problem attached to linear systems. What will happen when you have the same situation extended in the nonlinear system direction is completely open, of course. But already for linear systems, the full extent of the behavior to internal structure problem is a nonlinear problem. Which is one reason why it had a difficult history up to now. When this method was developed, there was also a big literature on algebraic geometry, and invariance can, of course, be applied to algebraic geometry, but unfortunately, the interpretation of the invariance was very unclear in geometric terms. So we now have the interesting fact that we have more interpretation of the invariance in terms of systems, such as the Bezout, the signature of the Bezout matrix, giving us exact information about what reactive elements a system contains. In spite of a great deal of sort of historical fog and confusion and change of directions, etc., there is a very good chance that this method will bring system theory to a much higher level of insight and make connections as there should be with also not only with engineering problems, which are very well known, but also with basic problems of physics, which in the opinion of many people is theoretically far behind what has been accomplished in system theory so far. My old and acquaintance, or maybe friend, Roger Penrose, once characterized the trends in modern physics by saying that, among other things, that quantum mechanics is called faith. It is not quite the same thing as physics. And now we have some particularly good reason to think that this situation gradually should change. Thank you very much for your attention.
Thanks very much, Professor Kalman, for these very nice insights from the outside, emphasizing invariant theory. We have time for questions, comments, and so on, if somebody has them. Of course, a look back with so much insight is very difficult to comment on, especially for the younger generation. So I suggest yeah, please use the microphone.
Professor Kalman, thank you for exciting lecture. Maybe I didn't catch the connection too well. Could you comment again about connection between the ideas you presented in this lecture and Kalman-Yakubovich lemma, how it is incorporated in all this context? Kalman-Yakubovich lemma, could you comment again?
Could you repeat? I have about 3/4 of the... Oh, yes, okay. Well, yes, the Kalman-Yakubovich lemma, Yakubovich-Kalman lemma, I would say, more accurately, inverse alphabetical order, not direct, is concerned with the question similar to what I discussed, namely, when is a linear system passive? That was historically related by Brune to the question of realizing, constructing a realization of an impedance which represents a passive, which comes from a passive system. That conclusion of Brune's work is unsatisfactory, although a high-level accomplishment, because it requires an ideal transformer, which is a passive system, but is a very different kind of a passive system than a resistor, capacitor, or inductor. In particular, if you take the atomic analogy, it's hard to think of an atom which contains an ideal transformer relating the three components of the three constituents of the atom. The second difficulty with that thing is that the invariant represented by the condition of Bruni is an irrational invariant, not a rational invariant. And much of the theory of invariance developed so far had to do with the rational case. So we have an additional mathematical difficulty in implementing a program, as I mentioned. Moreover, if we do it right, that is to say, without ideal transformers, the conditions so far obtained, for example, in the Ladenheim thesis, are very complicated, and it's difficult without a good deal of further mathematical work to put them in a closed form. In the case of Bruni, the so-called positive real condition was a relatively simple closed form, but it was mathematically, first of all, it solved a different problem, both from a practical and theoretical point of view, and second, it was not part of a developed theory, and therefore, even today, we know very little more about it than Bruni did 80 years ago. To answer your basic question, this thing is a side issue in the thing that I've discussed, and it is now, in my opinion, absolutely clear that the correct formulation goes via rational algebraic invariance in this case. So, in other words, you open up a huge territory because the previous attempts were not quite in the right direction. Now, of course, you can also, if you can do irrational invariance, of course, you can also proceed in that direction further.
Thank you.
Let me just say that I've been thinking about this problem for at least maybe 40 years, almost 50 years, and I found it very difficult to put the various things together on the basis of the existing literature, the books, and so forth. And therefore, this new way of organizing things is a major step forward to doing useful research in the future.
Thank you very much.
Roger, can you please also use the microphone?
I was amused by your suggestion that atoms might contain transformers. And I'd just like to point out that, in fact, nuclei can contain spin. And so Rabi's experiment in the 1930s to show that nuclear magnetic resonance was a real possibility is something you might want to consider if you also think about gyrators as well as transformers.
It was also mainly a comment that does not require an answer, right? So are there any other questions, comments you want to make? Then let us thank again very much Professor Rudolf Kalman for coming here. It was truly a great honor and pleasure for us having you here as the opening plenary speaker.